This is the first lecture from Chapter 15, and it's a continuation of our discussion of equilibrium, but it's with a focus on acids and bases. Acids and bases play a really important role in our lives, particularly in our bodies, and equilibrium of acids and bases in turn also play quite an important role. And so I think that's probably why it has a chapter devoted to it. First of all, to go over the definitions, properties, and structures of acids and bases. An acid, as we've learned when we learned how to name them, has a hydrogen atom that is directly bonded to an electronegative atom. Now remember, the atoms, the elements that are electronegative are the ones that are closest to fluorine, which is the most electronegative element on the periodic table. And so in order to be an acidic hydrogen, it has to be bonded to an electronegative atom. And if you were to draw partial charges for that bond, you can see now that the electronegative atom is hogging the 2 electrons that are used to make the bond, leaving this hydrogen atom electron deficient with a partial positive charge. So almost think of the bond, it's almost kind of started to separate a bit already. And so it's a little bit easier for this type of bond to serve as an acid rather than, for example, a carbon-hydrogen bond, which is a nonpolar bond. There's no separation of partial charges, and therefore the hydrogen's being held a little bit more tightly to the carbon. So some of the common acids that you will see, a lot of them, the hydrogens are bonded directly to an oxygen. Not all of them, but a lot of them you'll see. Here's hydrochloric acid, the beginning of acetic acid. Acids are characterized by a sour taste. As a matter of fact, so it's citric acid that gives kind of that bite in lemons and limes and even a little bit in oranges. Citric acid is also commonly used for the sour candy that they sell that's coated with like a sour powdery coating. That's citric acid usually too. Acids are pretty reactive actually. They dissolve with many metals, and that's why your car battery, for example, has sulfuric acid in it typically. And that's why your battery can get so corroded. That's why a lot of batteries can get corroded because there are acids in them. And of course, acids react with metals. And of course, acids react with bases. Acid-base reaction is called a neutralization reaction. And you may have played around with acids, bases, and pHs in high school chemistry lab, but acids turn litmus paper red. Some of the common acids, hydrochloric. Now remember, we learned how to name these, so you may need to refresh yourself on those. Sulfuric, nitric, acetic, which is what's in vinegar, citric, carbonic. That's important in your body, regulating the pH of your blood. Hydrofluoric acid, if you watch Breaking Bad, they filled a bathtub full of that, I think with the intention of dissolving a body, but instead they didn't realize that hydrofluoric acid reacts with ceramic and it chewed through the bathtub and caved the floor in. Phosphoric acid. Some properties of bases. They taste bitter, so they don't taste good. So mustard, that kind of taste to it, is a base. They feel slippery. So most cleaning products have some type of base in them, including soap, very weak base. But I don't know if you've ever read any historical pieces or novels, and they talk about, I think it was in early settlement days, like 1800s, if they took a bath, it's like a guy scrubbed with lye, because they used to literally just use like sodium hydroxide for soap. And bases turn litmus paper blue. And of course, as we said, they react with acids and neutralization reactions. Some common bases. sodium hydroxide, potassium hydroxide. So you will notice through this chapter that compounds that have the polyatomic hydroxide in them are often basic substances. Then we have things like bicarbonate, which is what baking soda is, sodium bicarbonate, or just plain old sodium carbonate. And then we have our weak base ammonia, which is also, as you know, in a lot of cleaning agents. So I'm going to present the original theory of acids and bases because it's still useful in some cases, and then I'll give you the more recent understanding or definition. So the original, which is the Arrhenius theory of acids and bases, said that acids would be anything that produced an H3O or hydronium ion in water. So the Arrhenius acids and bases both had to take place in water in order to be considered an acid or a base. And you'll see that our more recent definition expands. It doesn't have to be in water. So, for example, if you dump hydrochloric acid in water, what's going to happen 100% and immediately is the acidic hydrogen on HCl is going to transfer to a water molecule, and that's how we get the hydronium ion. And then, of course, what's left over from the original acid is the chloride ion. So remember, an acid is anything, we define an acid as something that has a hydrogen atom bonded directly to an electronegative atom. And you'll see that in acidic reaction, an acid donates a hydrogen ion to something else. So the Arrhenius definition of base was something that produces hydroxide ions. So we assume, we associate the hydronium ion with acidic solutions and the hydroxide ion with basic solutions. So why does the hydrogen ion that's donated by an acid, so let's just look at hydrochloric acid again, right? The reaction I showed on the previous slide showed this hydrogen ion being transferred to a water molecule to make hydronium, which is going to look funny to you there. It's usually written like that. And then you have chloride ion left over. So why don't we just see naked hydrogen ions floating around? They're too reactive. They're not stable. So immediately, if you're in aqueous solution, right, that little naked hydrogen ion is going to bond immediately with electronegative oxygen on a water molecule. But you will often see chemists will take a shortcut, and a lot of times they'll just write H plus with the understanding that their reading audience knows they mean H3O, so these are really considered equivalent. Now, a more recent definition of acids and bases is the Bronsted-Lowry. And that allowed us to include more substances of acids and bases. And so it didn't say anything about water. The definition of acid is pretty similar. It said is anything that donates a hydrogen ion to something else, okay? But it didn't say it has to produce H3O in aqueous solution, okay? But anything that donates a hydrogen ion. Now, why am I calling that a proton? So let me just diverge. Let's look at a hydrogen atom. A hydrogen atom has one proton and one electron. So, hydrogen atom, okay? What happens when I remove the one electron that it has? I get a hydrogen ion. But what's the only thing that's left? The only thing that's left is a proton. So a hydrogen ion is, in actuality, just a proton. So you will hear a lot of people, when they're talking about something that's acidic, they'll say it donated a proton instead of a hydrogen ion. All right, and then the Bronsted-Lowry definition of a base is anything that accepts a hydrogen ion, right? And then we will also be talking about reactions between acids and bases. So keep in mind these Bronsted-Lowry definitions. So here's a model of HCl, hydrochloric acid. And in an acid-base reaction, remember that an acid donates its acidic hydrogen, right? And a base accepts the proton or hydrogen ion. Now, you might wonder, like, how is this oxygen just making a third bond? Well, in order for something to serve as a base and accept a proton, a hydrogen ion, it has to have at least one lone pair. Why? Because you need to you're making a bond. You're making a new bond with a hydrogen ion, right? That hydrogen ion has no electrons. So whatever it's pairing with better have at least one lone pair that can be used to create a bond between the two atoms. And so, of course, then after the acid-base reaction happens, you're left with the remnants of the original acid. That'll be an anion. And then you're also left with a positively charged, whatever the base was. Okay, and we have terms for those, what they're really called. So before I get to that, though, there are some substances that can act as both an acid, that is a proton donor, and a base, a proton acceptor. And water's the most prevalent one. So you really need to know that vocabulary. I'm going to show you an example. So it depends what water's in the presence of, right? If water's in the presence of an acid, it's going to react as a base. Okay? So all those examples I've been showing you so far, water's been acting as a base. Remember, Bronsted-Lowry definition of a base is anything that accepts a proton. And you can see for this reaction, that's exactly what's happened. This water molecule has accepted a proton or hydrogen ion from hydrochloric acid, so it's a base. Now, on the other hand, water can also, if it's in the presence of a base, and you just kind of have to memorize this, that neutral nitrogen-containing compounds act as bases, typically. So remember, a base, first of all, it has to have at least one lone pair. Okay, neutral nitrogen-containing compounds do. And this base, ammonia, is going to serve as a hydrogen ion acceptor. So water's going to be the acid this time. It's going to donate one of its acidic hydrogens to the ammonia, right, to give this positively charged, and then what's left over from the original acid, in this case hydroxide. Water is the most common amphoteric substance. All right, so I told you we were going to name the products of an acid-base reaction. So generically, the substances formed from an acid-base reaction are called conjugate acid and conjugate base. So it's not hard, but the concept's a little odd, so you probably need to focus quite a bit on this. Make sure you understand it. All right, I'm going to walk you through the reaction we have here at the bottom and explain these definitions as I walk through the reaction. So let's look at conjugate base first. A conjugate base is a substance that is left over after an acid gives away its hydrogen ion, its proton. So let's look at this. Here's the acid, right? Nitrous acid. And it's going to give away its acidic hydrogen. And once it does give away the acidic hydrogen, in this case to water, what's left over, right, is called the conjugate base. So, if you start with an acid, you're going to get a conjugate base. That's why they're called conjugate acid-base pairs. Now, you're going to see if you start with the base, what it's going to produce is the conjugate acid. So an acid gives a conjugate base, a base gives a conjugate acid. So let's now look at the definition for conjugate acid. Conjugate acid is the product that is formed from a base after it accepts a proton. So here's our base, water, which means it's going to accept a proton. It's going to snatch this proton from nitrous acid. And what's formed when that base accepts a proton is called the conjugate acid. So the products are the conjugate acid base. Okay, and the original reactants are the original acid and base. So here's just another example that may be a little more simple to look at. Again, the original acid makes the conjugate base, and the original base makes the conjugate acid. Now, a typical multiple choice question might simply give you a reaction and ask you to label them as, and usually we use symbols, AB for acid base and CB for conjugate base, CA for conjugate acid. Or it may ask you to list all of the conjugate acid base pairs. So one of the pairs in this top reaction would be HNO2 with NO2 minus. That would be one pair. And it's just substances that where one comes from in the other one, or one forms the other one. Another pair would be H2O with hydronium ion. Those are the two conjugate acid base pairs. Now in the bottom reaction, see the base makes or turns into the conjugate acid. So that's one conjugate acid base pair. And then the acid turns into the conjugate base. So there's the second conjugate acid base pair. So you may need to, well, you will need to be able to identify them in a chemical equation like that, but you may also simply be given a substance and asked, what is the, if this is an acid, what is its conjugate base? What is the conjugate base of HCl? So this is a little weird. You need to practice this, and there are practice worksheets uploaded too. So what you have to go through in your head in figuring these out is saying, okay, this is an acid. What do acids do? Acids donate a proton, a hydrogen ion, right? So you go ahead and do the activity, do the action, and then what's left over is the conjugate base. Okay? So we're going to give away. So when you're dealing with an acid, give away that acidic hydrogen, and what's left is your conjugate base. So let's do it for the rest of the acids. Here's sulfuric acid. Let's give away one of its acidic hydrogens. What's left over is the conjugate base. We can do this two steps. There are two acidic hydrogens in sulfuric acid. So let's give away another acidic hydrogen, and this now is the conjugate base of HSO4 minus. Now, let me erase that because the rest of them, well, that's not true. The rest are acids too. Let's go in the other direction. That's what we're going to do. All right, so what if you start this way? Okay, so that's a base. It certainly is not an acid, right? There's no hydrogen period to donate. So, and you'll get familiar that most of the time when you have something with a negative charge, it can function as a base. So this is a base, which is a proton acceptor. So if this is a base, what is its conjugate acid? So again, you do the function that it's made for. That's a base. That means it accepts a hydrogen ion. So go ahead and add a hydrogen to it. And what's formed is the conjugate acid. So let's do that here too. There's a negative sign. That's a base. It's amphoteric, by the way, because that can serve as an acid too. But we're going to presume it's behaving as a base. What would its conjugate acid be? Well, make it act like a base. What do? You add a hydrogen ion, and there you go. There's its conjugate acid. Let's do that with a sulfate anion. Here's the base. What is its conjugate acid? Okay, well, what does a base do? It accepts a hydrogen ion. So there you go. Alrighty. See if you can get these two ones with water correct. Okay, so imagine water being a base. What would its conjugate acid be? And make sure you understand. and then go the other direction. Treat water as an acid. We know it can act either as an acid or base. And then ask yourself, what is the conjugate base of water? So be able to do all those, okay? Here's a little more practice, and then there are some for you to try also. Name and write the conjugate acid of each of these. So don't peek at the bottom of the page, okay? So if they're asking you for the conjugate acid, that means the stuff you're starting with is a base. What do bases do? They accept a hydrogen ion. All right, then just do what their definition says they do. Add a hydrogen ion. Now, you may have noticed by now that since hydrogen ions have a +1 charge, you've got to do charge conservation here. So if you're adding together a +1 charge to a -1 charge here, right, your resultant compound is going to be neutral. +1 - 1 is 0. So it's really important when doing acid-base reactions to keep up the charges. Again, all of these are acting as bases, all right? So when this acts as a base, in other words, when it accepts a hydrogen ion, what do you get? You get water. So water would be the conjugate acid for the hydroxide. Again, make sure you conservation of charge. Plus and minus makes no charge. Now, water, it said find the conjugate acid, so we're going to pretend like it's acting as a base. We're going to make it accept a hydrogen ion, and when it does, we get H3O. Now, what is the charge of H3O? Water has no charge, hydrogen ion has +1, so you have to maintain charge. So hydronium ion has +1 charge. What is the conjugate acid of this? Well, just add a hydrogen ion. Now again, conservation of charge. +1 and -1, so carbonic acid is neutral. All right, so again, do as much as you need to get comfortable with conjugate acids and bases. This is a similar type question, but it's asking you for the conjugate base, which means you're going to treat each of these as an acid and see what they form. And that just means you take off a hydrogen ion. Now, pay attention to the charge. That ends up being the trickiest part for students in acid-base reactions. If you take away an H+, which is what you're doing, what are you left with? Okay, so make sure that the conjugate base is going to have an additional negative charge than it had as the original acid. All right, so what's the conjugate base of here? Take away an H+, okay, and add a negative charge, so now it's CO3 2-. What is the conjugate base of sulfuric acid? Let's remove one of the acidic hydrogens, and you are left with this. And how about N2H5? So again, remove a hydrogen. Now be careful of the charge. You've removed a so this overall has a charge of +1. You're removing that plus along with the hydrogen. So what you're left over with is neutral N2H4. Another way to keep track of your charges is to write the H+ that you just removed. And make sure that when you add the charges of both the H+ you removed and what's left over, that when you add those charges together, in this case it's +1, that charge better be the same as what it was in the original compound. Conservation of charge. The rest of this lecture is going to be over pH and how to calculate pH and related terms. And so I want to give you just a brief little history lesson of where the concept of pH even came from. So most of the acidic acid-base reactions we're going to do are going to be in water. They're going to be aqueous reactions. And what's kind of interesting is that water itself ionizes with itself. And that's called autoionization of water. So even in pure neutral water, you will have a very small percentage of water molecules that will react with each other. One of them will function as a base and one of them will function as an acid. And so you get a very small percentage, but a measurable amount of the hydronium ion and hydroxide ion even in neutral water. And because you have equal amounts, like I've told you before, the hydronium ion is thought of as an acid and the hydroxide as a base, but because you have equal amounts of them, if you look at the balanced reaction, it's a 1-to-1 stoichiometry. So because you have equal amounts of these ions, you still have a neutral solution. But we can do quite a bit with the equilibrium expression and equilibrium constant for this reversible equilibrium reaction. So, as always, if we were to write the equilibrium expression for this reaction, products over reactants, right? Concentration of hydronium ion times concentration of hydroxide ion divided by, all of our reactants are liquids. Remember, those are not included in equilibrium expressions. So here is the entire equilibrium expression for this autoionization of water. And that is referred to as Kw. I told you there are a bunch of different Ks. What do we have? We have K, just generic equilibrium. We have Kc for concentration, Kp for pressures, and now we have Kw. At room temperature, which is 25 degrees Celsius or 298 Kelvin, the value for the Kw is 1 times 10 to the minus 14. Now that's an important value. So that's a value that you really should memorize, and you'll see in the next few slides why. But what that means, since that's measurable and we know that value, we can find out the concentration of either hydronium ion or hydroxide ion. We know that these two concentrations are equal, right, because of the stoichiometry of this reaction. And if they're equal, right, that means that the concentration of each one of them individually is 1 times 10 to the minus 7. So it's kind of obvious mathematically, but let's call the concentrations of each of these X. Okay, we know that they're equal to each other, so we're going to call both of them X. So we could rewrite the Kw expression like this. And then if you want to know the concentration of just one of them, we can do that by taking the square root, right? So X is the square root of 1 times 10 to the minus 14th, and the square root of that is 1 times 10 to the minus 7. So that's the concentration of both hydronium ion and hydroxide ion in neutral water. Not very much, right? Very, very low concentration. Alrighty. Now, this is always true at 25 degrees Celsius. Okay, remember, the only thing that changes in equilibrium constant value is temperature. So if you're at 25 degrees, Kw is always going to be there. That comes in handy, and that's really what the foundation and basis of pH is. So, for example, let's say that somebody dumped a little bit of basic solution, ammonia or something, in water. And they're not sure how much they dumped in, okay? But they have a piece of equipment that lets them know the hydrogen ion concentration. Now remember, I said chemists sometimes get lazy and say hydrogen ion, but what they mean, that's considered to be equivalent to this. They just get lazy and don't write out the whole hydronium formula. All right, so they know the hydronium ion concentration, and they can use that to find the concentration of hydroxide that they added, because we know Kw, right? As long as it's done at 25 degrees Celsius. So you just rearrange this equation to solve for hydroxide. So Let me rewrite that generically. So here's the expression that you need to remember. And that equals 1 times 10 to the minus 14. And so if you were trying to solve for hydroxide, which is what we're trying to do in this reaction, you could just rearrange this equation, and it would be equal to Kw over concentration of hydronium ion. Now we know Kw is 1 times 10 to the minus 14, and the problem gave us the hydronium concentration. All right, so that's where this comes from. So we're going to do a bunch of different, kind of simple, but a bunch of different calculations for hydronium ion concentration, hydroxide concentration, pH, pOH. So just make sure you do a bunch of practice so you don't get them. So what happens in an aqueous solution, okay, if you have water and you dump in an acid or a base, okay? So first of all, when it's neutral, if you haven't disturbed it with any acid or base, this is true, right? Equal concentrations. If you add an acid solution to some water, you're going to be increasing the hydronium ion concentration. Remember, because that's what acids do. They produce a hydronium ion. So when you increase the hydronium ion concentration, what happens to the hydroxide concentration automatically? Now remember, the product of the two has to be this constant, 1 times 10 to the minus 7. So if you increase hydronium, the hydroxide decreases automatically. They're inversely related. Okay? And now, same thing goes on. If we increase the hydroxide concentration, if we dump in a base, what's going to happen to the hydronium ion concentration? It'll go down. So well, scientists came up with a formula for pH, and I think everybody's familiar with pH. But let me tell you, just spend a minute on where this came from. Anytime you have log values, when you take the log of something, you're really just grabbing its exponent and bringing that down as kind of a digitized number. So 1 times 10 to the minus 2, for example, if you took the log of that number, it would just be 2. So you're just grabbing the exponents. Sorry, it'd be minus 2. You're just grabbing the exponents when you log. And so logs are usually used when you have very small or very large numbers, and it's quite cumbersome to write out scientific notation. And so that's all this pH is. We know that the concentration of hydronium ion is what's key to understanding how acidic a solution is. And so we could simply measure hydronium ion concentration, report it, but it's just easier instead of the scientific notation again. So we call, and you will notice that when you see a lowercase p in chemistry, it means minus log of something. All right, I think they used to call it power of hydrogen, whatever, it doesn't matter. But so pH is just a man-made definition, is the log of hydronium ion concentration, and that gives us a measure of acidity. Now, it's not just log, it's minus log, okay? I guess so they don't get as many minus numbers. So, you are probably familiar with this, but just to remind you, if you have an excess of hydronium ion in an aqueous solution, that means you have an acidic solution, and the pH will always be less than 7, right? So similarly, if you have a basic solution, which means you have a lower hydronium, or conversely, you could say you have a higher hydroxide concentration, then the pH will be greater than 7. So any pH greater than 7 is basic. Any pH less than 7 is acidic. And if the pH is exactly 7, it is neutral. Now, again, the pH scale is a logarithmic scale, and so it's basically, well, it is just taking the exponent down so that we don't have to keep writing scientific notation. And it's minus log, so that's why the minus sign on these exponents are going away. So low pHs are acidic, and so they have higher hydronium or hydrogen ion concentration. All right. Then solutions that have a high pH are basic, okay, which means they have a very low hydronium ion concentration, or much lower than the acidic side, see? So again, just notice that all these pH values actually represent the exponent of the hydronium ion concentration. Now, do you understand our pH scale now? Remember, pH of 7 means neutral. And what does neutral mean? Neutral means the concentration of hydronium ion equals the concentration of hydroxide. So where does that 7 come from? Remember what I said, that in a neutral solution, remember Kw is 1 times 10 to the minus 14. And in a neutral solution, that means both the hydronium ion and the hydroxide ion each equal 1 times 10 to the minus 7. So that's where 7 comes from as the pH of a neutral solution. So let's do some samples. Here's a straightforward. Calculate the pH, and they gave you the molarity of the hydronium ion. Very easy. All you have to do is remember the formula. pH is minus log of that hydrogen ion concentration. So find the log button on your calculator. Take the log of 0.0034, change the sign, and you should get 2.47. Okay, so that is an acidic solution. Now, you may be tempted to blow this off. Don't. This shows up on the standardized final too. The significant figures in a pH number are funky. Any digit to the left of the decimal, if you're talking about pHs, is not a Sig Fig. Remember, in order to be a significant figure, it has to be a measured value. Any digits to the left are simply the exponent. Just tells the magnitude. It's not a measured number. So only digits to the right of the decimal are Sig Figs. So why do we care? Because if you're asked to maintain Sig Figs, like chemistry likes you to do sometimes, you have to be aware of that. So how many Sig Figs does this concentration have? Well, remember that leading zeros are not significant figures. So this has 2 Sig Figs, which means your pH value better have 2 Sig Figs. So this does have 2 Sig Figs. Because remember, any numbers to the left of the decimal don't count as Sig Figs. So remember that little tidbit. That'll help you get 1 or 2 questions right on the. Let's go in the other direction. Let's say that they gave you pH. Instead of giving you hydrogen ion concentration, they give you pH. And they want you to calculate the hydrogen ion concentration. Okay? So now remember, these are considered equivalent to chemists. So how do we rearrange this equation for pH so that we can solve for hydronium ion concentration? How do we get rid of a log? Well, both sides become an exponent for 10. It's log base 10, right? Okay. So the 10 and the log cancel each other out. So what you end up with is concentration of hydronium ion is 10 raised to the minus pH. So again, you're going to be looking for a 10 to the X button on your calculator. And typically on my calculator anyway, I would put in the pH, okay, 3.52, and then hit the plus or minus sign. And then after that, I would punch a 10 to the X key. Now, every calculator is different, but make sure that when you think you have found the right calculator keys, that you get this for an answer. All right. Now, this is going to seem like circular reasoning, and it kind of is. You'll see in a minute. But what have we talked about so far? We have talked about concentration of hydronium ion, concentration of hydroxide ion, pH. Now we're going to talk about something pOH. Remember what I told you P means? P means minus log of anything. So pOH, what is pOH? It means minus log of the concentration of OH. And so whereas pH gives us the degree of acidity, pOH will give us the degree of basicity. So you can do the same type of calculations for that. What is the pOH of neutral water? Well, it's minus log of the concentration of hydroxide ion, okay, which is 7. Now, this is cool. This is where it gets to be kind of circular. The sum of pH plus pOH must equal 14. And that's because, remember this is true, okay? The product of the hydronium ion concentration times hydroxide ion concentration is always 1 times 10 to the minus 14th. Remember, that's kW. That's at 25 degrees. Okay. Now, we use this equality that we're familiar with now to get this equality, pH plus pOH equals 14. And we do that simply by taking minus log of both sides. Okay, this is what we get. So that's a pretty good. So that means if you know pOH, you automatically know pH and vice versa. I'm not sure what order I just said that in, but if you know one, you can find the other very easily. And so it's just kind of cool. So again, if you look at this little thing put together at the bottom, pH and pOH have to always add together to be 14, which is very cool. And again, as one goes up, the other goes down, right? And the sum of both of them always equals 14. Now, here's our circular logic. I love this chart. It may seem kind of busy and a little bit overwhelming, but this is one you may want to print out when you work through your worksheet, and pretty soon you'll just kind of know it, but you should work enough problems until you can do this do the problems without looking at this. So these are all the different values we've worked with in this PowerPoint, and they're all interrelated with each other. So if you have any one of them, you can find all of the others, okay? So just kind of a reminder, because here are the two equations everything's coming from. This is one of them. And then pH plus pOH is 14. So they basically just took these equations that we've practiced with and used them to interrelate all of these. So if you want to go from hydrogen ion, and remember we're seeing that as equivalent to hydronium, right, to hydroxide, you're going to use, let me change colors here. You are going to use this equation, right, kW. And so the concentration of the other one is going to be kW divided by the concentration of the one you know. So you can go back and forth from these using that equation. Now, if you have high concentration hydroxide, you can easily find pOH by doing the minus log of it. Same thing for the hydrogen ion going to pH, and going from pH to pOH is simply 14 minus the one you know will give you the other. And that is it for the first lecture in chapter 15. And next time, the next lecture will be about how to determine the strength of acids and bases.